Okay, so we're going to prove this big theorem about integrality. Implies that you have going up and lying over. Just for convenience, let me kind of scribble down. We have going up if and only if P is a prime of R. And that's just a complement that prime and Q is an ideal maximum with respect. With respect to Q intersect S, and then Q intersect R. And we also had kind of a similar thing for ink. So I just want us to call this, we did this proof. Ink holds if and only if P is a prime and Q and P is a prime such that Q intersect R. P then Q is maximal with respect to the exclusion of S. Complement of P and R. And here is kind of a big meat and potatoes one theorem. The rings with T interval over R. Then this pair is both lying over and going up, or I'm sorry, going up and eight. This is a big theorem, one of my favorites. So if you've got integrality, then you've got going up, and you've got ink as well. So. So we're going to use these characterizations that I have over here. We must show that so first we're going to show going up, use this characterization. If P is prime of R and Q is maximal with respect to the exclusion of S, then it contracts back to P. Suppose P and R is prime, S is R minus P, and Q in T is maximal such that Q intersect S. We need to show, of course, that Q intersect R. That is the goal, what we're trying to do. Note, we made this observation last time that certainly it's the case that Q intersect R is actually contained inside of it, right? Because Q misses everything that's outside of P, so its intersection down with R has to be inside of And of course, what we want is an equality here. So let's, by way of contradiction, let's suppose we can find some element X that lives in P, but is not in, Q intersect R. Well, what can you say about this ideal here? This is, of course, an ideal. Notice that X is, of course, an element of R, but of course, if it's an element of R, it's an element of T. So suppose we throw X into the mix up here with Q. Now Q is maximal with respect to missing S. So I don't know much, but I know that this properly contains Q, so it must pick up something in S, which is the complement of P and R. So it strictly contains Q, and so it's S. So there is this Q and maybe an A and T. So this is what a generic element of this ideal looks like. It's something in Q plus a multiple in T of something of X, and this must be some element of S. So so far I've not used any integrality here. All right. So here's where the integrality comes in. Since A is an element of T, it must be integral over R. And so I'll write this equation thusly. With each for in R. Right. So I'm going to multiply this by X to the N to get an equation of integrality for X to the N. So if I multiply it by X to the N, and notice X actually comes out of P, so it's an element of R. So this is still an equation of integrality for AX, right? Because X is actually an element of R, so this is just a bigger element of R, so forth, so on. And so what I'm going to do now is, let's see what we have here. AX is equal to S minus Q, right? Because of this equation right here. And so what I'm going to do is I'm going to replace AX by this. And I'm going to write this way. Right. So I'm going to replace each one of these. So I'm going to go quickly with my algebra. Now, of course, I can multiply this all out, big ugly binomial theorem. But what I'm gonna do is I'm gonna collect the powers of S first. So for sure, I'm gonna have this. X. I can certainly extract that because it's basically just the leading terms out of this expansion, the S to the n term, S to the n minus 1 term, and so forth. Do I agree? And I have this whole orgy of stuff that I've left out. But one thing that I noticed about everything I left out is it's got a factor of Q in it, right? Everything else has got a factor of Q. And so I'm going to write this as because what's left over all has a factor of Q in it, and Q is of course an element of prime ideal Q, right? So I'm just going to kind of write that way and not worry about what the form of Q is, just that it's in that ideal. So let's look at the left-hand side of this. Does anybody see what the problem is? So this side of the equation, we'll see this. This is in R. Right? And it's also in Q. Everybody agree with that? So this side of the equation is in B. Everybody agree? Because the whole thing is in R, it's in Q, and R intersect Q is contained inside of B somewhere. Right? What's the problem with that?
X is P, all of your terms except for the S N or S to the N are in P, so S to the N also has to be in P.
That is exactly right. So what we have is Sn plus X times, notice that I can pull a factor of X out of everything that's left over. And I'll just call that R. Is in P. Right? But this is in P as well. Right? Because X is in P. Therefore, S to the N is in P, which implies that S is in P, it's prime ideal. And this is a contradiction. Because by definition, S is the set complement. Hence, so R intersects P, and so by our earlier criterion, we must have building up. That's kind of cool, right? And we see how the integrality showed up. How about for the other one? Let's do the ink part of this. To establish ink, we also use earlier characterization. So let's assume that, so we're going to use this. We need to show that if P and R is prime and Q is a prime that contracts to it, then Q is maximal with respect to the exclusion of S. So assume but P and R and Q and T be primes such that P is equal to Q intercept R. Right, so we got that contraction there. We know we need to show that Q is maximal with respect to the exclusion of S. That is our goal, and that's how we will establish ink by our earlier characterization. Suppose not, so suppose that Q is properly contained in I. If not, then Q, if it's not maximal with respect to the exclusion of S, then it's properly contained in some ideal, bigger ideal. And notice we could even make I to be prime if we like. So let's pick something in I, but that is not in Q. And again, we're going to use the fact that this U that we selected is in fact integral. This was kind of a fun proof here. So suppose that Q is not maximal with respect to missing S, so I can put it inside a slightly bigger ideal that is that also misses S. Let U be something in that ideal side of Q. Now U is integral. Over R by hypothesis. And so what I'm going to do is I want to select among all polynomials that annihilate U. So among all polynomials in Rx, such that f of U is in Q. Now, I know that in fact, there is some polynomial such that f of U is 0, right? That's what it means to be integral. So there is some polynomial such that f of U is 0, and I'm going to generalize it slightly. I don't want to just consider polynomials such that f of U is 0. I want to generalize this to say polynomials such that f of U is in Q. This would, of course, include the minimal monic polynomial. We select one of least degree. And of course, the degree must be at least 1, right? Because the constant can't be in there. So let's suppose our polynomial looks like this. UN plus Rn minus 1, UN minus 1, Rn U plus R0. This is our minimal expression. This is the way polynomials are plugged in. This is our minimal expression such that sum is minimal with respect to the degree of that. note that. So this is in Q. What can you say about this? No, star zero. Can you justify that?
Contained in I, so to speak.
Right, right. So notice that this whole sum is contained in Q, right? And notice that U is contained in I, right? So the R zero actually must be an I. Right? So we have that so let me make this observation. So R zero is actually in I intersect R, because of course it's in R by definition, which is contained in P, which is contained in Q. So U times U to the n minus one, plus R n minus one, U to the n minus two, R one. This thing is in but U is not in Q by assumption, right? And why is that piece not in Q? By the minimality of this expression. So here you have a product of two things being in prime ideal with neither of the two being in the prime ideal. This is a contradiction as Q is prime. So Q is maximal with respect to Q intersect S is empty, and so R inside P is empty. That's kind of a groovy little proof there, I think. Okay, any questions? Here are a couple of small lemmas that once you see how to do it, it's not too difficult, and it paves the way for kind of a bigger theorem. These are both independent interests and use. Lemma 519, if R inside T is going up, then the dimension of R is less than or equal to the dimension. So whenever you have an extension that's going up, then the dimension tends to get bigger as you go up, so to speak. So suppose you have a chain prime at the R level. Yes. Okay. What I want to do is show the corresponding to any chain of primes I could ever build at the R level. I can actually build one at least that long at the T level. And this is just repeated application of going up. So at the R level, we have P0 inside P1. Now, going up implies lying over, right? I'm going to use that corollary. So at the T level, I'm guaranteed this by going up because it's lying over. So there's a Q0 that intersects down, right? Going up allows me to go up and build this. Right? Well, now I've got another prime. And now I've got Q1 that lies over P1. And this allows me to go up here. And you just keep extending this. And so what this shows is, if I walk up to you on the street and give you a chain of prime ideals at this level, you can lie over the bottom one and then use going up to build a ladder. So for every chain in white, I get a chain at least as long in yellow, right? So I mean, ink actually does the opposite. Ink squeezes the definition, or squeezes the dimension of the other. If R inside T is ink, then the dimension tends to get smaller as you go up. So let's do this the other way. Suppose you have a chain of primes at the T level. Say Q0, Q1, Q2, Q n minus 1, Qn. So suppose you have a chain of primes this way. It's easy to get change of primes at the lower level by just intersect. So just intersect down, and you get P0, P1. Now, let me point out that P0 is certainly contained in P1 in this respect, but what we got to be careful about is this is a strict jump. We need to make sure this is a strict jump. And it is precisely because of ink. Because what ink says is if you have no two comparable primes can lie over the same prime, right? That means that P1 is contained in P0, P0 is contained in P1, and that containment has to be strict, because if it's not strict, then you violate ink. And you keep going up like this, going up like bad choice of words. But again, this is ink, so these two intersect the comparable primes down here, and because of ink, they have to be distinct. And the strictness is all due to the fact that you can't have comparable primes intersect the same one. Everybody agree? So what that means is if I've got a chain of length n here, then I have to have a corresponding chain of at least n here, right? So when I take the supremum, I know that I've always got an orange chain that's greater than or equal to the length of the white chain. So dimension R is greater than or equal to the dimension of T. Everybody okay with that? So here is a corollary to all this that I will couch in terms of theorem. 5.11. Suppose R inside T satisfied going up and then the crawl dimensions are the same if you can get both going up and in. So corollary. Yeah, R inside P is integral. Then because in particular, any integral extension satisfies going up and in. And so the Kroll dimensions are the same. So for example, so let me kind of give you an application really quick. Let R proof that line. And an outbreak. So this is an outbreak extension here. If T is equal to the uniform closure of R and F, then T is proof. And the dimension of R equals the dimension of T. And this is our standard way to construct new domains from old, is to take an outbreak extension quotient field, you can build a bigger one. Well, we've got a bonus now because T is an integral extension of R by definition. And so it actually not only is a proofer, we already know that fact, but also it has the same Kroll dimension, right? So for example, in algebraic number theory, we often take R equals Z and F over quotient field of Z, which of course in this case is Q. We have finite extension, right? So when you did Galois theory, a lot of the energy went into that, and number theory, a lot of an algebraic number field is the interval closure of Z in a finite extension of rationals, then in this case, P is proofer, one-dimensional, and confined to theory. These two we know. The Noetherian, the reason it remains Noetherian is yet to be shown, but we will get to that. And this is actually called Dedekind domain. So any ring of integers that you encounter, it's got this really nice property. They are Dedekind domains. They're one-dimensional Noetherian proofer domains. Okay. Any questions? Math learns next door. Sounds like a game show, doesn't it? Dedekind domains. So actually, you can think of Dedekind domains as a generalization of a lot of things. In a certain sense, general, or you can think of it as a specialization of proof domains. In fact, what we're going to discover is Dedekind domains are exactly proof domains that are Noetherian. And let's see, what would you get for that? What does it mean to be proof? It means that every finitely generated ideal is invertible. Now, if you throw Noetherian onto that, that means that every ideal is finitely generated, right? Actually, I should say every finitely generated non-zero ideal is invertible. So if you throw Noetherian into this means that all non-zero ideals. So that's going to be a strong condition. So this actually, it turns out Dedekind domains are exactly proof domains that are Noetherian, and this really tightens things up. And there are a zillion equivalent characterizations of Dedekind domains in the literature. They show up all over the place. One can also think of it historically, I think, as a generalization of UFDs in the following sense. What does it mean to be a UFD? Well, it means that every non-zero non-unit factor is uniquely in primes, right? We actually had a characterization of UFDs earlier in this class that you're a UFD, if you're an integral domain, you're a UFD if and only if every non-zero prime ideal contains a non-zero prime element, right? One way of thinking about UFDs is all elements can be factored uniquely into primes. You can be fancy and think of that in terms of ideals in the following sense. Every non-zero principal ideal, let me rephrase. Every non-zero proper principal ideal can be factored into principal prime ideals, right? That's thinking about it in terms of ideals. I mean, that's basically the same thing as factorization, right? Unfortunately, with UFDs, it gets a little bit shaky when you leave the realm of principal ideals, right? So here's what part of the problem is. Here's kind of historically what happened. So everybody's familiar with Fermat's theorem, right? This is a big one, right? Or plane. this was kind of a holy grail for many years until Andrew Wiles. And Andrew Wiles got to the bottom of it, and laid the foundation. There was an error in what he first did, and then he kind of patched it up pretty quickly. People were certain when he first came out with it that it was the right idea. From himself, wrote in the margin of some book that he had found a nice solution to this. The margin was too small, some kind of stuff like this. But, and I will tell you that even after Wiles is proved, which, you know, all the lay people find very unsatisfying because, you know, you have to use pretty sophisticated machinery. So there are probably still people out there looking for that two-page proof, right? And if you do find a two-page proof from Wiles' theorem, Harvard's going to give you a PhD in math, right? But don't do it. It's much easier to write a 2,000-page math than to do that. So historically, and let me point out what I mean by non-trivial solutions is if I let y be 0, there's obviously solutions to this, right? So what happened with this thing? Well, first of all, I think that Fermat himself knew that he was mistaken with his first thing because later in his life he proved some special cases, and after all, he had a general case. Why would he bother doing special cases? The case for n equals 4 is actually of interest. It uses a technique called infinite descent in number theory. It's kind of a fun one. But so here's what happened. People started chipping away at this thing, and they reduced it to this. It suffices to establish this claim or it suffices, you can show that it suffices to do it for the prime. So people started looking at this. And this yielded some fruit. And then, you know, this was proven the case for P equals 3, P equals 5. People kind of chipped away at it. And then there was a proof given in 1847 that proved this in general for primes, assuming where this thing is P primitive P root. So you might think of and so what is this ring here? It turns out that this is in fact the integral closure of Z. So here's what you do. You take Z inside of Q, you take this finite extension by adjoining this P through unity. This is an extension of degree P. This is Galois for those of you that are paying for 8520 and nice in that respect. And it turns out that if you take the integral closure of Z in this, you exactly get this ring. This is the integral closure of Z in this. So what do we know? We know it's proof of domain, one-dimensional. If you believe what I said earlier, it's in theory, and it's very nice. Very nice ring, one dimensional. Unfortunately. Not always. Oh, this was a step forward. So here's the problem. This actually works. First failure of unique factorization. Does anybody know what it is? Smallest prime for which this fails. 22, the smallest prime. For which so this actually got a lot of cases from laws I see, but oops, it falls apart at 23. After 23, some things do happen. And actually, kind of historically, what happened after this is it turned out that you didn't quite need unique factorization here. You needed something called a regular prime. And what that means is the prime, it's regular if the prime does not divide the order of the class group. Right, P does not divide the order of the class group of this thing, which, so they define these primes to be regular primes, and if it's, so if the prime is regular, they could also prove Fermat's theorem. Fermat's theorem is, of course, since fallen. However, what is not known is it turns out that it is known now, and the latest that I've read about this, it is known that there are actually infinitely many irregular primes, but it's not known that there's infinitely many regular primes, which means that the terminology is probably a little bit premature. However, what failed in this proof is they were taking this thing, treating them like polynomials and factoring them. And they factored this using roots of unity in a very clever way. And they said, oh, look, unique factorization works out. And so we've got Fermat's theorem. And somebody pointed out, how do you know that that's the only way to factor this? They say, you know, that's unique factorization. Well, oops, that's where the slip was there. So Dedekind domains, which we're going to talk about, in one sense, were sort of motivated by this failure, because what happens in Dedekind domains is you do not necessarily have unique factorization in the primes of your elements. What you do have, and this is true here as well, is you have that every non-zero proper ideal factors uniquely into prime ideals. So it's sort of the next best thing. You possibly lose the fact that your elements can factor into prime elements. What you gain is every ideal can be factored uniquely into prime ideals. Notice that when these two properties coincide, what you have is principal ideal domain, as a matter of fact. And so Dedekind domains, in one sense, historically can be considered as sort of repairing this failure right here. The loss of unique factorization in elements can be recovered a little bit by trying to factor ideals uniquely into prime ideals. And we'll see how some of that works next time. Any questions? All right, you all have a good one. Remember, I've got a meeting that I have to attend, but I'll be free at 11 o'clock, good Lord willing. So y'all have a good one, and we'll see you on Friday.